from the studios of Postscript Media and Canary Media.
I'm Shayle Kann, and this is Catalyst.
Once you get to cost below $1,000 or 1,000 euros per kilo to low Earth orbit, then you're getting into the ballpark where this could be economically viable. And we're not far off from that.
Space-based solar power. Need I say more?
Catalyst is brought to you by The Antenna Group, the OGs of climatech PR and marketing. For 25 years, Antenna Group has partnered with category-leading energy transition and clean economy innovators to build their brands, amplify their stories, and market and accelerate business growth. As climate tech moves from the age of innovation to the age of adoption, the stakes are different now, and they're a lot bigger. And there's never been a better time for your brand to leave its mark. If you're a startup, an investor, enterprise, or innovation ecosystem that's creating positive change, Antenna Group is ready to power your impact. Visit antennagroup.com to learn more. Catalyst is brought to you by RE+. RE Plus Events is headed back to Las Vegas from September 11th through the 14th at the Venetian Convention Center and Expo. It's the biggest B2B clean energy event in North America, featuring solar, energy storage, hydrogen, fuel cells, and more. They're bringing the energy industry together to create a cleaner future for all, and you can learn from top business leaders across the industry. Catalyst listeners, here's a treat. Use promo code CATALYST20 to get 20% off an Expo Pass. Hurry and register at re-plus.com. That's re-plus.com.
If you're enjoying Catalyst, there's another show that I think you'd really like. It's called Freakonomics Radio. I'm sure many of you have heard of it. It has over 10 years and 500 episodes worth of answers to your wonkiest questions about science and technology and more, with a good bit of business and economic insight thrown in. They have a new batch of episodes that explores the ins and outs of the whaling industry with economists and environmental activists and historians. It's really interesting. The host, as you may know, is the best-selling author Stephen Dubner, and he dives into questions like, how did whales go from economic engines to environmental icons? So don't miss out. Listen to Freakonomics Radio every week, wherever you get your podcasts, and tell them I sent you. I'm Shayle Kann. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. All right. I mean, listen, obviously this is crazy, but also maybe it's not totally crazy. Anyway, the idea is to beam concentrated solar power from space down to receivers on Earth. If you could do that at scale, economically, you'd get 24/7 solar anywhere on Earth at any time. In fact, you could move that power from one place on Earth to another place on Earth with no power losses in between at any point in time. That's the pitch. And clearly it sounds like science fiction. In fact, the origins of it are science fiction. But to be fair, nuclear fusion also sounds like science fiction, and we're pouring lots of resources into that these days. And with space-based solar, there is a case to be made that we should be paying attention. Largely because I think the biggest barriers, and to be clear, I'm saying biggest, but not only, have been the cost of getting lots and lots of stuff into space and then assembling that stuff in a way that makes it useful. And those barriers are changing as the space economy emerges. Also, there is some real activity in space-based solar coming predominantly from government agencies, but also a few private sector actors. So, to get the lay of the land, the lay of the space, I guess, I spoke to Sanjay Vijendran, who is the lead for the Solaris initiative on space-based solar power at the European Space Agency. So, beam us up, Scotty. Sorry. Very, very sorry. Sanjay, welcome.
Hi, thanks for having me on the show.
I cannot wait to talk to you about space-based solar power. It's a topic I've been learning about for the past, 12 months, something like that, and find fascinating and really confusing. So let's start with the basics. What is the concept of space-based solar power at the high level, and what's the promise of it?
Okay, so the easiest way to think of this is an advanced form of solar power. So take your solar panels that you're well used to, and think of putting it in a place where you can get the most pure form of solar energy at the highest intensity where it's always available. And that's just simply not available on Earth. And the best place, and the only place you can do that, is up in orbit in space. So far enough away from the Earth at a high enough orbit, you can see the sun 24/7, and the intensity of the sun is the maximum, unfiltered by the atmosphere. And there you can collect solar energy from our sun in the best way possible. Of course, the big challenge is how do you get it down to the Earth if you want to use it on the surface of the Earth? And that's where power beaming, wireless power beaming comes in, up and coming capability to send electricity from space down to the Earth. So put your solar farm up in space, deliver the energy down to the Earth. That's what space-based solar power is about.
Right. And so the promise here is, as you said, 24/7 solar. So it solves solar's intermittency issue. And theoretically, depending on a variety of components of cost, which we're going to talk through, you could deliver, the belief is that you could deliver that 24/7 clean energy cost effectively, right? So that it falls into this category, ultimately, if you could do it, falls into the category of these other like clean, firm, renewable or clean, firm resources like nuclear power or geothermal or, other things like that can deliver 24/7, zero emissions, hopefully cost-effective power.
Yes, that's absolutely the main value proposition here. So to be able to get green baseload power into the grid, you don't have very many options available to you on the surface of the Earth. You've mentioned some of them, nuclear fusion. This is what nuclear fusion promises, if and when it ever comes. Geothermal, to some extent hydro, but even things like hydropower, which is what we have today, it is weather dependent and climate dependent. With space-based solar power, this is really offering you a weather independent 24/7 source of clean power that's coming from an inexhaustible resource, and you basically solve the problem of intermittency without the need for storage. And that's really the big offering here.
The other key difference with hydropower and geothermal, at least today, is that those are location dependent too. So I assume in principle, space-based solar power, you are in orbit as you are collecting the solar power, but then you're beaming it and you can beam it theoretically anywhere on Earth. Is that true?
That's right. So this is another key offering, in that any country, no matter where you are on the planet, as long as you have the technology to be able to put these collecting systems up in space and can put the receivers down on the ground where you need them, then you have access to this resource essentially equally, because it's not dependent on the geography and the resource availability on the surface of the Earth like solar and wind is.
Okay, so very exciting, but obviously we've never done it. So in the same vein as nuclear fusion, this is a potential energy source, not an actual one at this point. And so I want to talk through what it might take to make this a reality. But before we get into the future, let's talk about the past a little bit, because the idea of space-based solar power is not new. In fact, I'm old enough to remember that Pacific Gas and Electric, the utility in Northern California, actually signed a PPA for space-based solar in, I don't know, you could probably tell me in like 2009 or something like that. That obviously
yes, it was around then.
Never went anywhere, but I remember that PPA. So maybe just walk me through the history of space-based solar power, and then we can get into like why this resurgence in interest now, what's changing, and what do the technologies have to look like?
Sure. So it is an old idea. It actually goes back all the way to 1941 when Isaac Asimov wrote about it in one of his science fiction stories, where there was a manned space station that was beaming power to planetary bodies through the use of radio frequencies. So collecting energy in space and sending it at a distance away. But it wasn't until the late 60s when the idea was really thought about from a technical point of view. How would you go about doing this? And a gentleman called Peter Glaser in the US, working for Arthur D. Little, came up with the first technical concepts of how you would collect energy in space and deliver that down to the ground. And he actually patented it in the early 1970s as well. And then it was in the 70s oil crisis that hit the world, especially the Western world, and the US and others were scrambling in those early years of the 70s to find alternative sources to fossil fuels. That's when the big investment into other forms of energy, including nuclear fission and space-based solar power, happened. And the Department of Energy in the US and NASA jointly did some substantial studies at that time to understand what the promise and the challenges of space-based solar power were. And the conclusions at the time were that this is likely technically doable. It would really help provide a substantial source of energy that would be affordable once the costs could be brought down to a level to make it economically competitive. And the cost drivers at the time were the costs of launching things into space and the cost of the space hardware and how you would assemble it. Of course, in the 1970s, we were very far away from reusable launches at that point. And we were also very far away from thinking about how we could assemble with robots huge structures up in space. The space shuttle was being developed, astronauts were the way things were being put together. So the economic case at that time couldn't be made by far. And that's why once the oil crisis was over in the early 80s and fossil fuels became affordable again, the whole idea was shelved because it just seemed to be not economically competitive, even if it was technically doable. And every 10 years or so, NASA, as well as Europe, the European Space Agency, has looked again at the topic, done a cost-benefit analysis, looked at the latest designs of how you might put these things together in space using the latest technologies. And the conclusions have repeatedly essentially been the same. This is technically doable, it would be useful if it could be done, but it's just too expensive right now. And that is what was the last conclusion, even by the European Space Agency that looked at this in the mid-2000s. And only the last 10 years has really brought about a big change in some of these key cost drivers, thanks to the advent of reusable launches and the mass production of satellite hardware that we're seeing now employed in low Earth orbit constellations for telecommunications. So these are fundamental changes that have really changed the economics of space-based solar power.
Yeah, I want to get back to the economics and those drivers that sort of what do you have to believe that this is going to be economic. But let's talk about the technical side of it for a moment first. So as I think about it, here are the sort of stages of things that need to happen in order for space-based solar power to be a thing. You need to launch a bunch of hardware into orbit. That hardware needs to be solar collectors, solar panels of some sort or another, right, to gather the solar energy. That stuff needs to sit in orbit and be controlled, assembled and controlled, collect solar energy. Then you need to beam that power down to somewhere on Earth. So you have this wireless power beaming problem, which you described already. And there needs to be a receiver sitting somewhere on Earth that collects that beamed power. That's basically the steps. So in terms of the technical challenge, can you sort of walk me through how much is proven about each of those components? What's the hard part? What's the easiest part? What are the unknowns? And then we'll get into the economics from there.
Sure. So the first thing to be aware of is that from a physics perspective, in terms of what is exactly happening going from sunlight all the way to electricity into the grid, every step along the way is something that we know how to do from a physics point of view. And we've been doing it already for 60 years in space. So a space-based solar power system is essentially an extremely large telecommunication satellite, because that's what all telecommunication satellites do today. They take sunlight, they convert it to electricity, they then convert it to radio frequencies, they put it through a huge antenna, they send a beam of signals down to the Earth, which are collected, radio frequency signals, and converted into information in the form of electricity in your mobile devices and other things. So step by step, this is not new science or new physics that needs to be invented to figure out how we can do this. The big challenge is the scale that this needs to be employed at in order to make it useful for power provision purposes to the Earth, and especially for the Earth market versus, say, the Moon or Mars or in-space power beaming, where beaming kilowatts of power to other satellites or a megawatt of power to the surface of the moon, for example, would be extremely useful to have because they have zero in power infrastructure today. But for the Earth, if you're going to provide power into the grid, for example, you're talking about hundreds of megawatts or a gigawatt worth of power to basically replace a coal or a nuclear power station. So if you're going to do it and make it useful, then it's going to need to be done at an extremely large scale. And because the sun is limited to, even up in space, 1.4 kilowatts per square meter, whichever way you cut it, you have to have a huge collection area. We're talking about 10 square kilometers worth of collection area or more. That's like a very large solar farm that you see in the countryside, but you've got to put that up into space. And then you've got to put that radio frequency energy, once you convert it from electricity into RF, through a huge antenna to be able to make a shaped, controllable, directable beam down to the surface of the Earth where there's a receiver and collect all of that power. And because of the way physics works out for radio frequencies, the size of the antenna determines the size of the receiver that's on the ground, and it depends on the frequency and the distance between the satellite and the surface of the Earth. And it's an inverse relationship. So if you want to have a receiver that is of a reasonable size on the ground, that's not too large, let's say a few kilometers in diameter, then you still need to have an antenna in space that is 1 to 2 kilometers in diameter, depending on the frequency. But whichever way, even at a high end of the frequency range you could choose, we're talking hundreds of meters to a kilometer. So these are huge structures. The largest thing anyone's ever put into space, humanity's put into space, is the International Space Station, and that's only 100 meters across. So we're talking about something that's an order of magnitude in dimensions larger than anything we've done before. And when you total up the amount of mass that's involved, we're talking about thousands of tons of mass of hardware to put up into space, to assemble robotically, and to control it. You have to be able to control this as a single structure and point it to where it needs to point safely, and collect all of that power with the receiver. So it's an engineering challenge to do the launching at the high cadence, at the low cost, enough launches in a reasonable time to get all that hardware up into the right orbit, and then another engineering challenge to have the robotic systems that are going to put these together safely and properly with limited human supervision, and then controlling the satellite, doing the power conversion, handling all this thermal energy that will be produced, because there's always some losses along the way on each of the steps, and then having a receiver that's a few kilometers in diameter on the ground as well, that has to be laid out and to collect the power and feed it into the grid. So these are some of the main challenges, and then there's the technical and economic challenge of making all of this economically affordable as well.
So you described what I've learned about this is you've got a bunch of technical challenges. None of them break the laws of physics, but they're real, like serious engineering challenges. Getting all this hardware into space, ridiculous amount of hardware into space, assembling it all, and so on. The one thing you didn't mention, though, is the actual power beaming component. Where are we in the trajectory of being able to beam power wirelessly? Like, what have we proven there? What is the most power that has been beamed and over what distance? Because again, here we're going to be talking about hundreds of megawatts to potentially gigawatts of power being beamed over obviously an extremely long distance.
Sure. So indeed, power beaming is probably the most science fiction part of the whole thing to people who've first heard about space-based solar power, because people can imagine solar farms, they're familiar with them, putting them up in space, robotic assembly. Those are all things that people are already doing at a smaller scale. But power beaming is not something we deal with really in our everyday life, and most people, I myself a few years ago, wasn't aware that it really is a thing. It's been a thing since the time Nikola Tesla, over 100 years ago, thought about how power could be sent wirelessly, and imagined having huge towers that could send power around the world. And he looked into the theory of it, and he never managed to make it practical. But across the decades, people all around the world have been doing small-scale experiments showing that power can be sent wirelessly with using microwaves, radio frequencies, to be able to power things like aerial vehicles, sending power to balloons, obviously on the desktop, up to kilowatts of power, tens of kilowatts even, was shown by the Jet Propulsion Laboratory and Raytheon company in the 1970s in California. They did an experiment where they sent 30 kilowatts of power across a distance of over a kilometer and collected a lot of that power. So power beaming is possible. People have demonstrated it at various scales. In the kilowatt range, in the kilometer distance is what has been achieved so far. So what we now need to get to is to beam this power in a similar configuration to how we would be doing it from space to the Earth. So not using monolithic kind of radar dishes, as people have done often in the past, but using what's called phased array antennas, so flat plate systems that are made up of lots of modular parts that can be put together like Lego, and you have to control millions and ultimately billions of individual antennas to be able to all work together to form a single shaped beam to send power to the air, to space. And people are starting to now commercialize that for terrestrial applications already, because there is value in being able to send some megawatts of power across a kilometer distance and avoid having to put cables down in, for example, extreme terrains or undersea cables from offshore wind farms to onshore grid, for example. There's going to be a commercial market for power beaming technology terrestrially, and the technologies needed to make that happen will be basically the building blocks that we'll use for space power beaming once it's scaled up to a larger scale. So we're seeing companies get into that area already now, and these are the ones that are readying the capability to be used from space to Earth in the future.
So again, maybe further along than people who haven't been paying attention might realize, but at the same time, if I was hearing you right, sort of what's been demonstrated thus far is hundreds of kilowatts over a sort of, let's call it a kilometer distance. And what we will need for economic space-based solar power would be hundreds of megawatts over thousands of kilometers distance, right? So orders of magnitude more power, orders of magnitude more distance in any case. And so do you think of that as being, is this going to be like a steady progression to get to that point? Or are there, I guess, what are the technical limitations? Why can't we deliver 10 megawatts of power 100 kilometers on land today?
It's not a issue of we can't do it today. People haven't tried to do it yet. It's not that people have put together these systems and found it too challenging and have failed to do it. There hasn't been the push to invest in demonstrations at that scale yet, and that's for a number of reasons. Because the terrestrial market for power beaming has only just started. People have only started really thinking about it for terrestrial use fairly recently. The idea of beaming power from space to Earth is much older than terrestrial power beaming, and because as I said about the scale, it's been so daunting for so long and never on paper made the economic case for people to get the investment to try to do it at the scale of a megawatt over 10 kilometers or 100 kilometers on the Earth as a demonstration, because they could not justify that full-scale application. So raising the funding, the R&D, to do substantial power beaming technology development has been too challenging all across the world, whether it's Europe, the US. But now as the idea of the full-scale application with the pressures of climate change and looking for alternative solutions, people are becoming more open-minded about taking on this huge challenge because the payoff is so large. And some people have been successful more than others at raising some funding, whether it's the US military or Caltech in the US or in China and Europe. We're trying to do the same with our Solaris program to the European Space Agency. We're now starting to be able to raise some significant level of R&D funding to try to demonstrate these larger scale demonstrations of power beaming. So, of course, as you scale things up, even though we know how to beam power at this few meter size antenna, a kilometer distance, the theory is going to be essentially the same to go up to higher power levels and larger distances. But once you start working on the practical systems of trying to make such a large antenna and coordinate such large numbers of individual antennas and things like that, you'll come into problems you haven't foreseen that come in through this attempt to increase the scalability of it. So how do we upscale? This is a challenge for all new tech. You can demonstrate it in the lab, but when you get out in the real world, you need to scale it up an order of magnitude or 3 orders of magnitude, and then new problems come in as you start to do that. So I think it's just people haven't tried it yet because they haven't been able to justify why should we try to take on this huge challenge when there's other alternatives, or at least perceived to be other alternatives.
Catalyst is brought to you by Antenna Group. Antenna Group is the largest integrated marketing and public relations agency dedicated to the energy transition and clean economy. It represents a portfolio of over 75 category-leading companies across solar, storage, smart grid, EVs, electrification, carbon capture, sustainable materials, decarbonization, and beyond. They've been at it for 25 years before clean tech was even a word. They've built some of the largest brands in the industry along the way. With unmatched domain expertise and global teams led by industry insiders, Antenna Group is on the front lines helping climate tech companies with go-to-market strategy, public relations, digital marketing, and much more. If your company is looking to win the hearts of investors, customers, influencers, or strategic partners, look no further than Antenna Group. These guys are also hiring like crazy, so for all you climate communications warriors out there, go to antennagroup.com to check out job openings or to work with them on your PR strategy. Catalyst is brought to you by RE+. Mark your calendars for September 11th through the 14th and join your colleagues at the Venetian Convention Center and Expo. This isn't your average event. It's the largest B2B clean energy extravaganza in all of North America. Brace yourself for a mind-bogglingly large showcase of solar power, energy storage, hydrogen, fuel cells, grid edge technologies, EVs, and more. RE+ Events is on a mission to unite the energy industry in a quest for a cleaner future. We're talking about a massive gathering of innovative minds and forward-thinking companies who are revolutionizing the way we power our world. And we've got an exclusive discount for all you Catalyst listeners. Use promo code CANARY20 and enjoy a 20% discount on an Expo Pass. Don't miss your chance to immerse yourself in the latest advancements and network with industry leaders. Hurry over to re-plus.com to learn more about this transformative event. Secure your spot. Again, re-plus.com.
The other question that I've gotten a lot when talking about this, the power beaming part of this, is safety. What do we know about the safety of beaming that amount of power from space or on land for that matter? And what are the mitigants to avoid any safety concerns?
So this is, of course, a paramount issue, and no system would be deployed until it's been proven to be safe under all conditions. So we're designing safety into the system from the get-go, so that we can make sure that everything is under all conditions always going to be within safety limits. So radio frequencies. So one of the things we're doing is deliberately minimizing or reducing the intensity of the power that is in the beam to levels that are safe. So where we know the beam would be exposing, or people or animals would be exposed to parts of the beam, these intensity levels will be below the regulations and limits for such use of radio frequencies, which exists because we have these frequencies we use are similar to Wi-Fi and mobile phone systems. So there's a lot of work that's been done around the world about safety of different levels of watts per meter squared of radio frequencies in this gigahertz range that we're talking about. And the idea would be to make sure that any unrestricted regions around the receiver will have intensity levels which are within these safety limits. Now, in order to get sufficient power down to the ground without having too large a receiver, we do need to have a reasonable level of intensity. So part of the beam, especially the central part of the beam, will likely be exceeding safety limits up to perhaps a couple of 100 watts per square meter. And so while this exceeds the human exposure safety limit, the idea would be that the parts of the receiver that exceed the safety limit will be restricted entry, just like it is around nuclear power stations and other places where public entry is not allowed. So there will be fences and restricted zones. But the key thing is that even at 200 watts per square meter, for example, which is about a fifth of natural sunlight on a very sunny day at the equator, if you were to climb a fence and go into the center of this beam at 200 watts per square meter, we're not talking about anyone getting fried instantly. It's not extremely hazardous, instantly damaging kind of power. The only known effect from the research that's been done on these frequencies on human living tissue is heating. So you would feel warmer if you're standing in the beam, just like you'd feel warmer standing in the hot sun. But there's, of course, a lot more research that needs to be done to really pin down what are the short-term and long-term effects that may happen on flora, fauna, humans, and all of that. And that's work we plan to do still.
Let's transition to talking about costs. So obviously we've described this monumental feat of engineering that would have to occur in order to deliver that power from space to land. What are the things that we need to believe about the cost components in order to end up in a place where this could deliver power that we believe is economic? To the extent that you can use numbers, that's even better. Like what do launch costs have to be, and where are they today? What are the big hardware costs we need to be thinking about? Like what drives the economics here?
So what's historically driven and continues to drive the economics are two to three major things. So first is the launch costs, because of the sheer amount of hardware that needs to be put into space. That's a major driver. And secondly is the cost of the hardware itself, because there's a lot of hardware that's involved here. And space hardware has historically been rather expensive per kilogram. So these two factors in the past have been a killer for the economics, because we were assuming expendable launches and we were assuming hand-built, low production rate space hardware. And so that's what's made this a no-go in the past economically, but is fundamentally changing now. And we've seen an existence proof now from what SpaceX in particular have done in the last decade with the Falcon rockets and with Starlink and others are doing with constellations like OneWeb. They've shown that reusable launches can and do bring down costs massively. And this generation of reusable launches has already brought costs down by almost a couple of orders of magnitude from where they were with the space shuttle, for example. And people are developing even bigger high cadence heavy lift launches that, if and when they're successful, are going to bring the cost down by another order of magnitude. So we're talking a few orders of magnitude reduction in launch costs, and the economics, the cost benefit studies for space-based solar power have shown in the past that once you get to costs below $1,000 or 1,000 euros per kilo to low Earth orbit, then you're getting into the ballpark where this could be economically viable. And we're not far off from that. And potentially, if something like Starship or the equivalent really works out as planned, we could get to the mid hundreds or low hundreds or even less per kilo to low Earth orbit. So that's one metric, one target that we have to make this work. And we're seeing that there is a path in the next decade to reach that. So that's really good news. The second thing is the space hardware cost. It used to cost hundreds of thousands per kilogram of space hardware for scientific missions, all hand-built over a long period of time. Now we're talking about people who are building thousands of identical spacecraft on a factory line using consumer electronics or automotive industry mass production techniques to build space hardware. And that's brought the cost of space hardware down to of the order of $1,000 or so per kilogram as well, from where it used to be an order of two magnitudes higher. So when you combine these two cost reductions that we've seen on the space hardware and the launches, you are basically, for the same size and design of space-based solar power system that existed 30 years ago to ones that we're looking at now, the costs have fallen by orders of magnitude, really. So what was 100 billion before, now you're looking at 1 to 10 billion for a full system, depending on the scale you're looking at. And of course, there's also the cost to do with operations and maintenance and the assembly of the system with the robotics, which are a little bit less easy to figure out at the moment because people haven't really demonstrated that yet. But the latest analyses from not just from Europe but others around the world have shown that there really is a path now to seeing how this can be economically viable in a reasonable time frame. We're not talking about 20, 40, 50 years anymore. We're talking about 10 to 15 years. And there is proof that these numbers, these assumptions, projections that we are making in our analyses now are realistic, realizable assumptions and no more just wishful thinking as it has been in the past. So that's why the time for space-based solar power, we really believe, is now in a way that it hasn't been in the past because of these fundamental changes that have happened from other industries that are spinning in to make this now possible. And of course, if space-based solar power goes ahead with the scale of this industry, because if you're going to build one of these satellites, you're going to build many of them. A single power station is not adding to too much. The scale of this industry is going to be absolutely enormous because energy is the number one commercial industry in the world. It's a multi-trillion a year industry. If we tap even a small fraction of that market with space energy, and space energy from space, it's absolutely huge. And so that's going to end up actually driving the technology development and the mass production and of launches of space hardware, solar arrays. All of these things are going to end up being driven by this application, and that's going to cause much more investment and a reduction in costs as well. So it's going to be a positive feedback that comes simply because the scale of this is so huge, and then there's a whole load of infrastructure that's required in space for the logistics of moving things around, in orbit servicing, assembly, maintenance, disposal, refueling. All of these industries are not new. They're starting to happen for other purposes, but at much smaller scale. So again, space-based solar power will utilize those capabilities, but drive them into a much larger scale deployment as well.
Let's talk about where this industry, to the extent that it's an industry, is today. Who is working on space-based solar power, whether public or private sector? And what do you think of as being the sort of key milestones or demonstrations that we're expecting to see over the coming years?
Sure. So there have been a number of players for the last decades, national agencies like NASA way back, and then periodically, as I mentioned before, has looked at this. The European Space Agency has. The Japanese Space Agency has had a long-term, relatively modest level, but consistent level of technology development in this on this topic for a long time. And the UK, the United Kingdom, has recently also got into the game as well. So that's on the national side, and private industry has in the US. There are a couple of entities. Caltech is one that has got private funding from a donation about 10 years ago to work on space-based solar power, and they launched just this year a bunch of technology demonstrations into orbit and announced some weeks ago the results, some some positive results from their power beaming experiments in space that they did with that. And there's another privately funded company called Virtus Solis in the US that is also working on deploying space-based solar power in this decade as well. So we're starting to see increased efforts globally from a national perspective. And I haven't mentioned China. China has also in the last 5 years made announcements towards putting gigawatt scale space-based solar power systems into orbit by 2050 with demonstrations planned later this decade. So they are moving forward and recognizing the value of expanding all forms of renewable capability energy systems that are available, including space-based solar power. And Japan is intending to do a demonstration in 2025. So they've just announced that they've got funding to work on a demo mission, and these are subscale demos.
What are these demos that we're starting to see?
So what we've seen from the US side, both with Caltech and the Naval Research Laboratory in 2020 also launched some technology demonstrations into space. What we've seen so far are small scale technology demos in space without any major space to ground power beaming demonstration done yet, at least as far as we're aware. So what we do need to see as a next step, now that people are demonstrating that power beaming can happen in space and they're showing that their technology works in the space environment, is to start seeing a subscale demo of a full end-to-end system. So collecting power in space and using the right type of antenna and beaming that down to the ground and trying to collect most of that energy on the ground and use it for something useful. So that's the kind of end-to-end demonstration that hasn't been done, and we need to see that being done to give people a warm feeling that the whole, all the steps of the process can work within the Earth environment. And I think this is what is being planned by a number of people in 2025 timeframe, including the Japanese Space Agency, the US military, the Air Force Research Laboratory has a program that intends to put a demonstrator in orbit as well in that timeframe, and private companies as well. So there are demos we're going to see in the coming years at subscale that are showing in principle this can work. We'll of course find out some new challenges through such demonstrations, but hopefully through a positive outlook from these demos, people will start to see that this is now a proof of existence is there, and now it's a case of scaling up from an engineering perspective to larger scale demos, pilot plants, and eventually the full scale systems that we would like to deploy at scale.
Yeah, that was actually going to be my final question for you, which is, in your mind, what's a realistic time frame we should be expecting here? How long will it take to get from where we are today to the potential for, let's just say, the first commercial scale, commercial relevant scale space-based solar project?
So when we talk about commercial scale, we typically think in the order of 100 megawatts upwards. So this is the size of a typical large solar power plant that you get on Earth, up to 1 to 2 gigawatts, which is the top end of nuclear power stations. So that's the range we'll be talking about. And when people ask, how long will it be when this is ready? This is really depends on how much we're willing to invest in it. Peculiarly, space-based solar power is the only really promising form of clean energy, potential form of clean energy technology that I would argue the world is not investing in significantly, because every other energy source that you can think of, whether it's wave power, geothermal, nuclear fusion, all of these, and when I say geothermal, I'm talking about really deep geothermal where they're trying to go to 15 kilometers. All of these things can and are being and should be, of course, invested in, but space-based solar power is receiving almost no appreciable investment right now. So the activities I've mentioned, they are ongoing from around the world, but the levels of investment are not huge, and not commensurate with what we ought to be spending to really try to find out whether such a promising energy source as this is really is viable in the next 10, 15 years, and whether it can help us meeting our net zero goals for 2050. So there is the pace of the development is really driven now by the level of funding, which is not yet receiving. So if we carry on at this rate, it can be a very long time before we see anything. We do need to up it. Just to put it in context, nuclear fusion, which many regard as being decades away still, and government programs have on their roadmap for it to be not ready till the second half of this century, are yet receiving today billions per year in funding, and have been for a long time, and will continue to do so. And space-based solar power has all of the benefits of fusion, and some, because it can move power from one place to another place that is underneath a satellite, essentially instantly over vast geographic regions without any loss. And even nuclear fusion couldn't do that. You couldn't send power from, say, Berlin down to Cape Town just by moving the beam without any loss. And space-based solar power can do that. So we're talking about a decade, probably at the minimum, if there's a real push to make this happen, a moonshot-like approach, putting a substantial amount of funding over that amount of time to do the R&D, as well as the demos that you have to do along the way, because we're not going to be developing the technology and then deploying a full-scale gigawatt system in one go. So we'd expect to see a small-scale demo, maybe 100-megawatt pilot plant, and then eventually a scaling up to the gigawatt scale. Now, there are private companies that are ambitiously aiming for even a commercial scale 100-megawatt system by the end of this decade, but we'll have to see whether anything like that is really possible. But even if it ends up being in the middle of the next decade, we have the opportunity to scale this up in the late 2030s into the 2040s to help close that gap in clean energy that the world is definitely going to have, and a crucial gap as well, which is not the easy part, which can be filled by terrestrial solar and wind and some level of storage and demand side reduction, but that really difficult last bit of the consistent baseload firm power that we're going to be probably stuck on fossil fuels for longer if we didn't have a direct replacement in terms of clean, firm 24/7 power. That is available anywhere in the world. So this is where we're really aiming for, helping that energy transition to happen. And as I said, if it happens, if we can get the first systems in place by the mid 2030s to the late 2030s, that's still possibly helpful in terms of that time frame for helping complete the transition to a fully renewable future.
Well, Sanjay, this was fascinating, and I'm excited to see all these announcements that are forthcoming on these demonstrations that sound like we'll be hearing about over the next couple of years. So we'll bring you back on when we've got some more tangible evidence of feasibility to point to. But in the meantime, thank you so much for spending the time.
You're welcome. My pleasure. Thank you.
Sanjay Vijendran is the lead for the Solaris initiative on space-based solar power at the European Space Agency. This show is a co-production of Postscript Media and Canary Media. I also want to thank Will Lipscomb on my team at EIP, who's been diving deep into the world of space-based solar power and was very helpful here. This show is a co-production of Postscript Media and Canary Media. You can head over to canarymedia.com for links to topics on today's show. Postscript is supported by Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and ag, transportation and logistics, advanced materials and manufacturing, and advanced computing. This episode was produced by Daniel Waldorf. Mixing by Roy Campanella and Sean Marquand. Theme song by Sean Marquand. I'm Shayle Kann, and this is Catalyst.